Okay, I am recording and we're on this computer. Let's see, I want to have the chat show up so you can holler at me when I forget to switch the view back to whatever we're working with. And okay, happy Monday, Alex and Juan. Um, Gonna be moving a little bit forward. I should ask first if you have any questions on the homework or anything like that. I'm hoping today, I'm about halfway through grading the gravity homework, and I want to grade the first optics homework later today as well. So um, you'll be able to see that. Tomorrow in class for the lab, we're going to do let's see, it's a kind of a dry lab. It's a computer exercise, actually. You'll be given some data for a pattern of interference and diffraction. And then from that, you're going to figure out how wide was the slit and how far it's a two slit pattern, how far apart were the two slits. So um, lots of work in Excel on this one, but should be able to get it worked out. Students have managed to do this in the past. So we'll see how that goes. I think first today I'm going to change our view to something here. There it is, screen one, and show you something. These are some figures that are out of your textbook, and it's going to be looking at the intensity pattern for two slits of finite width, which is actually what we're going to be doing in the lab tomorrow, although it won't be exactly the same geometry as what they have here. But the picture you're looking at here shows the intensity for a single slit diffraction pattern. And this would be for a slit of width A. And I'll try to show you one of these tomorrow. I think I may have last week. I can't remember, but I want to get it set up better than I had it last week because it just wasn't being very clear when we were looking at it. Maybe if I put the laser in the back of the room, it might work out a little better. But you have a central maximum, and then it fades down to 0. And it'll do this either side of the central maximum. And then it'll come back a little bit, and then it'll drop down to 0 a bit. And sometimes you can see a few more places where it comes back, but it always diminishes in brightness. And so the central maximum is much brighter than the secondary maximum here, and then continuing on like that. So that's a single slit pattern. Back when we studied two slit interference, we ended up with an expression that more or less told us that we'd have minima at certain distance, and this is one where the separation between the two slits is 4 times the picture that you were just looking at. But anyway, that would predict that we'd have no diminishing in the brightness of the secondary maxima that we get out there. And it's just continuing to go out there like that. This has a few labels for the M values here. With the two slit pattern, we have that D sine theta equals M lambda is where you see bright fringes or maxima. And so this is where M is equal to 4. This is where M is equal to 8. And you can also have -4 and -8. It works out the same way anyway. But this isn't what we see if we actually have both an interference and a diffraction pattern. This, what you're looking at right now, the red, is the mathematical prediction, but this does not take into account diffraction. This is just taking into account interference. And when we actually consider diffraction, what we end up with is that we see something like this, where the red on here, and I hope it's coming through as red, is showing you the two-slit interference pattern, but it's being controlled by the purple line here, which is the intensity of the single-slit diffraction. And so you end up with the red waviness fading out to zero, controlled by the single slit diffraction, and then it'll come back again, but they never get as bright as they were toward the center maximum there. And so this is kind of what you actually see, that the intensity ends up being the product. That means mathematically multiplying things together of the two-slit pattern times the single-slit intensity. And so you end up with something like that. And then the last picture here, I don't remember which page this is on in your book, but it's in the chapter on diffraction. Anyway, here's the actual photograph of a pattern like that we just saw, where it's got the geometry where the two slits are separated by 4 times the width of the single slit. And you can see in here in the center, the very center one here would be the central maximum. And then you get some maxima either side of that are nearly as bright, but then it just disappears on you. And this is where it's controlled by that single slit diffraction stuff, where it just drops down to zero at certain points and then never comes back as strong. So that's what's going on with this stuff. So that's the first thing that I wanted to look at, was just those pictures, to try and keep in mind what we're actually seeing in a two-slit pattern. So let's see, I'll bring the sharing back to here, and we're back on the visualizer. Okay, so we have that going. I wanted to revisit something. Actually, what I want to do is talk about diffraction gratings a bit today. I can do a demonstration with those tomorrow, and also then consider the circular apertures and how that stuff might work out. And there is somewhere on the internet, there used to be a downloadable app that I could stick on my computer that showed a circular aperture diffraction pattern, actually a pair of them. And I've been hunting all over and I can't find it anymore. It's probably still out there, but there's so much more out there now than there used to be that there's lots of wrong alleys that I can turn down. But anyway, let's go back to considering some phase diagrams and phasor diagrams. And these are those things where I was drawing, for instance, when we considered the two-slit pattern, when I developed the expression for the intensity of a two-slit pattern, I did something where I sketched things like this, and this was maybe the electric field of one of the slits being produced at some observing point. This was the electric field of another slit, and maybe each of these has a magnitude of E naught. But I said that this angle is omega t, and then this angle up here is, this would be a phase difference between light from the adjacent slits. This is still omega t here. And so this total angle here is omega t plus 5. But when we consider the projection of these things over here on this vertical axis, that would be, let's see, yeah, this would be E1 sine of omega t, or maybe E naught sine omega t. This would be E naught sine of omega t plus phi. And the combined electric field then was the due to the length of this vector here. And um, we did a bunch of math, but you could imagine you'll have maxima anytime you can get phi, the phase angle between the adjacent slits, to be 0 or 2 pi or 4 pi or 6 pi. And so we could have things like that. So maxima when phi is equal to 0, that's the central maximum, 2 pi, 4 pi, dot, 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 and so forth. Now, again, this is ignoring diffraction effects, the single slit stuff that's going on. So that was a 2-slit pattern. I also did something with a 3-slit pattern last Tuesday when we met live. I was making some sketches about this for those 2-slit patterns. The intensity of these things, of this one, the 2-slit pattern, when we have 0 or 2 pi or 4 pi, it predicts that they'll all be the same intensity as the central maximum because we're ignoring diffraction effects. And so that's something. Now, if you have a 3-slit pattern, this is something that I sketched last week. So maybe here's the electric field from one of them, and we figured out that it's possible to have, well, what we saw was when we had a 3-slit pattern was that there's a bright central maximum, and this is just an intensity graph, and then there would be a smaller maximum, and then there'd be a bright central maximum again, and a smaller maximum, and a bright, not the central maximum, but a secondary maximum of some sort. And this was the pattern, and it continued on moving outward from there. Well, we can understand with a phasor diagram where that comes from, that this complete disappearance is something that happens when we have, let's see, the first one happens like this. It happens when you have a phase difference between the adjacent slits that is 2/3 pi. So, okay, or 120 degrees. Then they completely cancel each other out. And that's what that is. Now, this secondary maximum happens when what we have happening is two of the waves completely, or two of the light from two of the slits completely cancels out, but the light from the third slit is left over. And so we'll have something with the electric field strength being just 1/3 of the intensity of the central one, because two of them have knocked themselves out, and the electric field is just 1/3 of that value, but the intensity goes with the square of the electric field. And what we find out in that case is that this is just 1/9 the intensity. If this has an intensity here of I naught, this one has an intensity of just 1/9 I naught, because when you square 1/3, you get 1/9. Well, what happens when we have 4 slits? Okay, well, if you've got 4 slits, you can have your first complete zero when you've got a 90-degree phase difference. Here it was 120 degrees, or 2/3 of pi. Here it's 1/2 of pi is what happens when it first drops down to 0. Then you can have a secondary thing showing up when three of these things cancel each other out. That'd be at 2/3 pi. And if you do that again, you get 2/3 pi every time. But this would be three of them knocking each other out, or these three knocking each other out, and one that's left over. So, um, and I know this is kind of hard to follow, but remember, we've got four slits here. Three of them knock each other out, and one of them is left. Okay. Well, that means the electric field strength when you have a four-slit pattern on a secondary one, and so we'll make a boundary here. We'll have a bright central maximum, and then it'll drop to zero, and there'll be a little maximum or a little bright spot here, and actually there'll be two of these little bright spots, and you can monkey with the diagram to figure that out. And then it'll come back up to here, but the intensity of this one, if this has an intensity of I naught, this one is going to be 1/16 I naught. Okay. So when we had three slits, we had 1/9 I naught for the secondary. When we had four, we had 1/16. If we had five slits, it would actually be down to 1/25. If you had six, it'd be down to 1/36. And it keeps getting lower and lower in between here. And after a while, you're going to have things so faint in between here that you can't even see these anymore. If you had just say a dozen, a dozen slits, the intensity of this would end up being 1/144th the intensity of these. And you probably couldn't see them, which brings us to something called the diffraction grating. And the diffraction grating is something that used to be the way they made them was it would be a reflection grating, and they'd have a smoothly polished metal surface, and they would cut scratches into it that were very narrow and spaced very close together. Nowadays, they make them a transparent thing where they have a whole bunch, a large number of parallel slits and a very large number of parallel slits. On something. And what'll happen is you can shine a laser beam on one of these diffraction gratings, and the spot of the laser beam, maybe it's 3 or 4 millimeters, but this thing might have hundreds of parallel slits in a millimeter, or maybe dozens. But anyway, if you've got a spot that's, I don't know, 8 centimeters or 8 millimeters in diameter, it'll illuminate hundreds of these things. And basically, you end up with maxima occurring at the usual spot for parallel slits, which is d sine theta is equal to m lambda, where d is the separation between these parallel slits, but it ends up being extremely small is the value of that, and it makes the maxima occur at larger angles. And so when that's the case, you can just have a few spots of illumination on the thing. There'd be an m=0 spot in the center. There'd be a m=1 spot either side of it, and maybe another m=1 spot that's even farther out from that. But that's all you'll see. And in between them, you're just not seeing any light at all. So that's what you can see with a diffraction grating. And I'll show you a demonstration of that tomorrow. Diffraction gratings are neat. You can hold them up to your eye and see the, well, we did it one day, saw the illumination of the fluorescent lights in the room where you actually see that it's 3 or 4 separate colors in there that it's producing, and lots of different things. But anyway, that's the diffraction grating. And you end up with M equaling 0 plus or minus 1 plus or minus 2 dot 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 and so forth. Something else about diffraction gratings, because these parallel slits are so very close together, the slits themselves are very narrow. And here's something with a single slit pattern. Now, remember, with the single slit diffraction pattern, we ended up with an expression that looked like this: A sine theta equaling m lambda. This was where minima occurs. Okay, this is maxima up here. And that's the case for a diffraction grating. It's also the case if you just have a 2-slit pattern or a 3-slit pattern or something like that. We get the maxima showing up here. But with the single slit diffraction going on, we get minima here. However, if you look at this, what if you make A extremely narrow, as it will be in a diffraction grating? Well, the more narrow you make A, the larger the sine of theta will have to be in order to see these things. In fact, you can solve for sine of theta will equal m times lambda over A. And the biggest the value of the sine of theta can be is 1. Well, what if your slit width is about equal to the wavelength of the light? You'll never see anything. Okay, the m equal 1 value. Okay, remember m can be 0, 1, 2, 3, so forth. But if your slit width is about equal to the wavelength of the light, if it's much larger, then if A is much larger than lambda, then this will be a very small number, and you can have M be up to 1, 2, 3, 4, 5, as long as this right side isn't larger than 1, you can see maximum there. But if lambda over A is equal to 1, the very first maximum you could see beyond the central maximum would have a value of 1, and that means your sine of theta is going to equal 1, and it'll be out there at 90 degrees. You won't be able to see it. So, oh, and here I should say make A very narrow. So that's something that can happen. And with diffraction gratings, the actual slit widths on the thing can be so narrow that you'll never see a diffraction effect. And so all you'll see is uh, interference between these very large numbers of parallel slits, and all you'll see is this kind of thing going on. So let's do a couple of problems having to do with the diffraction grating and just see what happens here. We start off with monochromatic light is at normal incidence on a plane transmission grating. When we say transmission, it means light travels through it, and that's how you see the diffraction grating. There's also reflection gratings where light bounces off something and you see this. But it says the first order maximum in the interference pattern is at an angle of 8.94 degrees. What is the angular position of the fourth order maximum? Well, we go back to our equation for the diffraction grating that we have d sine theta is equal to m lambda. So just write that down here. Okay. And it says the first order maximum is at an angle of 8.94 degrees. Okay, well, we don't even know the spacing between these things, and we don't know what the light is, but we do know that the first order maximum is happening at 8.94 degrees. So this is saying that d times the sine of 8.94 degrees is just equal to lambda. So we may not be able to figure out everything else, but we can figure out lambda over d. And so sine of 8.94 degrees is equal to lambda divided by the slit spacing. And maybe just knowing that, we can work this stuff out. Now, where in the world did I put my calculator? Oh, there's the little. Let's see, am I in degrees? Yes, I am. So, oops, back. It's 9. Whoa, I don't know what's going on here. Help. Wow, I must have pushed a button to take myself all the way to the top of all the calculations I've done. Anyway, sine of 8.94. Okay, and that's 0.155. We can keep 3 sig figs on there. So that'll be good. So that's lambda over d. Well, what's the angular position of the fourth order magnitude? Well, for that, I would have the sine of um, theta is going to be 4 times lambda over d. So I just multiply that by 4 times 4, and that'll equal 0.622. So theta is going to be whatever the inverse sine of that happens to be. It's like 38.4 degrees. Okay, so that's pretty widely spread out from this thing. Now, is there a maximum? Could I possibly have, actually, with 0.155, I could get all the way up to 6, I would think. So let's figure out where the sixth order maximum happens to be. And so for that, I'd have the sine of, this would be theta sub 4, call this theta sub 6. It's going to be 6 times lambda over d, which is 6 times 0.155. That'd be at 0.93. And I could not possibly have a seventh order one, because if I multiply this by 7, I end up with a number bigger than 1, and I can't have a sine value bigger than 1. So this would be the last one visible. And this would be out at theta sub 6 will be out at 68.4 degrees. So we could go out that far, but that's it. I would not be able to see anything beyond that. So what we'd have in this case is actually, if you had the trend, or the grating right here, you'd see something straight ahead, we calculated the fourth order maximum out at about 38 degrees, which is going to be out roughly here. And in between, there'd be a second and a third order one. And then a bit farther out, you'd see a fifth order one. And at 68.4 degrees, we'd see a sixth one. And that's on one side. You'd see just the same thing on the other side, but that's it. You wouldn't see anything beyond that. So that's what'll happen in that case. Okay. What's this one? The wavelength range of the visible spectrum is approximately 380 to 750 nanometers. We've often been approximating it as 400 to 700 nanometers, but we can pretend that, or let's just use the more precise range here. White light, which is a mixture of all those wavelengths, falls at normal incidence on a diffraction grating that has 350 slits per millimeter. Okay, well, with 350 slits per millimeter and a centimeter, you'll have 10 times that many. So you'd have 3,500 slits between my fingers here. They're a centimeter apart. So that's how close together these things are. And then the slits themselves can be very narrow. Find the angular width of the visible spectrum in the first order and the third order. Okay, well, let's imagine what's going on here. Here's our slit. We've got white light falling onto this. It's not a slit, it's a diffraction grating falling onto this. And straight ahead, we'd have a central maximum. But then, and that straight ahead one is just going to have white light because all the colors will be in phase at that central maximum. But then we'll have some kind of a spread for the first order. Okay, now here's what's going to be happening here. For that first order, we'll have d sine theta is going to equal, it's just going to be, well, in general, it's m lambda, but for the first order one, we would just have d sine theta is equal to lambda. Excuse me. And the wave or the angle actually depends on the wavelength. So for the shorter wavelengths of violet light, 380 nanometers, the angle would be smaller. And then for the red, it's going to be larger. But let's go ahead and figure out what's going on here. Now, this 350 slits per millimeter, that's not the separation between the slits. It's actually the reciprocal of the separation between the slits. And so the D ends up being 1 divided by 350 slits over 1 times 10 to the minus third meters, or it'll be 1 times 10 to the minus third meters divided by 350, and whatever that ends up being, 1 EE minus 3 divided by, okay, the distance between the slits ends up being 2.8. We've only got 2 sig figs here, times 10 to the minus 6th meters. And that's how far it is between adjacent slits. Okay, that's not a whole lot bigger than the wavelength of light. Let's see. Actually, 750 nanometers is 0.75 times 10 to the minus 6 meters. So this doesn't tell us how wide the slits themselves are, but so we've got that anyway. And let's figure out for that first order maximum there, and we'll make a column for that. We would have the sine of theta violet is going to equal just lambda, the wavelength of the violet light, divided by d, just divided by d. So let's go ahead and toss the numbers in here. And 380 times 10 to the minus ninth meters divided by 2.8 times 10 to the minus sixth meters. And I'll figure this out in degrees just for the heck of it. But whoops. Actually, this is about 2.9. Should be 2.9 times 10 to the minus sixth. Then I get about 0.13. So that angle will end up being, let's see, I am in degrees. Or about 7.5 degrees. So that's where the violet shows up. Where does the red show up? Well, I just do the same calculation, and actually I'll write it out as one thing. I would have um, it's the angle for which the sine is going to be lambda for the red divided by that 2.9 times 10 to the minus sixth meters. So the red is 750. And let's see what we get. And I'd get out at about, well, 15.0 degrees. So spread between 7.5 degrees and 15 degrees away from this thing, you'd be able to see all the colors of the visible part of the spectrum, from violet here to red way over here, and everything in between there. So that'd work out pretty well. Okay, well, let's figure out the fourth order. The only thing different in the fourth order is that we'd be sticking a 4 into here. So I'm going to write down, I'd have the angle for which the sine is 4 times the wavelength divided by d. And I just divided both sides of the equation by the d and took the inverse sine of it. And so for the red, in the fourth order thing, we'd have, it'd be the inverse sine of 4 times the wavelengths of, whoops, I did the red first. Oh, well, that doesn't matter. 750 times 10 to the minus ninth meters divided by, it's the same D that we had before, 2.9 times 10 to the minus 6 meters. And that angle for the red, well, I'll do it down here. Let's see. Inverse sine again. And to repeat this calculation, I'm just going to go into my calculator and change those digits from 750 into 380. Oh, I got a domain error on this one. Oh, they said third order. Okay, I misread that. Yeah, you won't see the fourth, at least not the red part of it. So I have to change that 4 into a 3, which is easy enough. Okay. When I change that 4 to a 3, I get 51 degrees is actually what I get for the red. And for the violet on that third order one, I would just go in and change 750 into 380. And I get 23 degrees for that one. So um, it may be that sometimes you end up with some of these things overlapping with things. Like I would guess if I did the second order one, um, not sure just how it would work out. But anyway, this is quite a large spread. 23 degrees to 51 degrees. That's spread over, what, 28 degrees? And so that's where your rainbow, and if you've got a viewing surface that's quite a ways away, then you can have those spread over a fairly large distance. One time I was down in Arizona, and my wife and I had driven up to Kitt Peak Observatory, and we were down there on a vacation, and I like going to astronomical sites whenever I can, and it's a pretty nice observatory, a lot of different telescopes sitting up there on top of that mountain. And Arizona has lighting ordinances that even though the city of Tucson is not very far away, it doesn't produce much light pollution. And they do that so they can keep that business of having people come and build observatories near their cities. But anyway, we were up there on Kitt Peak, and one of the things they have up there is a solar telescope. It's one that just is aimed at the sun all the time. And it seems to me they had a 60-inch mirror, which is plenty big when you're looking at the sun to gather a lot of light. And then they take the light that comes in from the sun, hits that 60-inch mirror, and they feed it down a tube that they've got built in such a way that it doesn't have any convection currents in it, or they're minimized at least. But then they have it hit a reflection grating. That's like a diffraction grating, but it's on a mirror instead of a flat surface. And they take the visible spectrum of the sun and they have it spread out over about a 90-foot length of table, and you can just stand there and look at this thing and study different parts of it. It's really interesting to see all the absorption lines that showed up in that thing. That's something that we may learn about. You might have learned about that in chemistry, but anyway, it was kind of amazing to be there. And I actually, most people don't get to go down there, but when my wife and I were walking around, there was this tour going by, and I don't know how I happened to start talking to the tour guide. I guess they were just looking at something else at the time, but he found out that I taught astronomy and physics, and he said, "Oh, come join our tour." I said, "Okay, sounds good to me." Anyway, there's a little bit more about diffraction gratings. Okay, now on to circular apertures, and we'll just do one problem having to do with this today, but and somehow I need to track down the animation. If I hope it's still available out on the internet somewhere. But anyway, if you take light and shine it through a round hole, you don't get a nice smooth pattern, just like shining light through a narrow slit or through a pair of slits. You don't get something that would be produced if the light just traveled straight ahead, but you get these interference and diffraction effects. And when you do it for a round hole, you'll end up with a bright kind of central spot, and then it'll fade out and you'll have a dark region here, and then it'll come back, but you end up with kind of a bullseye pattern. And it's similar to if you actually looked from the side and maybe started at the very center of this thing and had a light sensor moving along here, you'd find out that it drops down to 0 and then comes back lower and comes back lower. And it does that in every direction now. And so you get this kind of bullseye pattern showing up there. And I should be able to get that set up so you can see it easily tomorrow. And I think I'll, instead of using the green laser, I've got a helium neon laser that I can, it actually runs off AC. And so I'll set it up back there so it's just left on, and we'll deal with that. But anyway, you get this bullseye pattern, and that's what happens. Now, the first minimum that shows up over here depends on a couple of things. It depends on the wavelength of the light, and it also depends on the diameter of the aperture that you're shining the light through. And the larger the diameter of the aperture is, the more tightly bunched this stuff is going to be. And so that's one of the effects that happens. But the longer the wavelength of the light, the more widely spread it's going to be. And so that's something that happens with this. Now, this becomes a concern in astronomy if you're looking at two light sources through your circular aperture. You might have the diffraction patterns like this of two different stars starting to overlap with each other. And if they happen to be, and it's not just in astronomy, actually, it shows up in other effects, but if they're so close together that the maximum of one star ends up showing up on the first minimum of the other star, you won't be able to tell them apart. When you actually add the light from the two sources together, you'll end up with something that looks like that, and you won't be able to distinguish them. And the rule that's generally given for this is that 1.22 lambda divided by the diameter of the aperture is where the first minimum shows up. And so you might call this theta min or something like that. But if you're making a diagram like this, where you're just kind of plotting the max or the brightness as a function of lambda in either direction, and it could be plus or minus lambda, the first minimum shows up at about 1.22 times the wavelength divided by the diameter of the aperture. And so if you've got things that are separated by exactly that angle, you have a really hard time telling them apart. If you start getting them farther apart, you'll be able to have it work better. This is sometimes called the, if I spell his name right, um, the Rayleigh, that's GH, criterion. And it's just how a way of trying to, Rayleigh was a guy who studied light and optics and stuff like that. And he sort of pointed this out that if you got things closer together than this angle, you're not going to be able to know that there are actually two objects there. So that's the thing. And let's see how this works. And I'll do some more problems with this tomorrow, probably. Let's see. Okay, so we've got a binary star system in the constellation of Orion. Has an angular separation between the two stars of 1.00 times 10 to the minus fifth radians. If lambda is 545 nanometers, what's the smallest diameter telescope that can just resolve the two stars? By the way, it's this effect that is one of the major reasons that astronomical telescopes are built so large. Okay? Because the larger you make it, the more ability you will have to see detail and not have things due to the diffraction effect just get blurred together. The other major reason is because the bigger you make the mirrors, the more light you can gather. And in astronomy, a lot of times the things that, well, the farther away things are, the fainter they get. And so um, there isn't, people don't much study planets, at least not solar system planets, with a telescope so much anymore. Instead, we send spacecraft out there to learn even more. However, what we'll have is our theta min is going to be 1.22 times the wavelength. Oh, by the way, this theta min is going to be in radians. And divided by the diameter. But we know the separation between these two stars. It's 1 times 10 to the minus fifth radians. So let's just solve for D here. D is going to be 1.22 times lambda, which is 545 times 10 to the minus ninth meters. And I've got 1 times 10 to the minus fifth radians there. And we get, I don't know what we get. Um, whoops, I didn't want that. Oh, heck, could have done this in our heads. Oh, well, I get about, if I didn't screw up any calculations, 545 times 10, yep, 1 times 10 to the minus fifth. I get 6.6 times 10 to the minus 2 meters. Well, how big a telescope is that? Not very big. It's only about that big. So that's about 3 inches in diameter. Okay. That's one of the cheapest amateur telescopes you could get, might have a diameter of that. That's pretty small. I actually have some binoculars that have bigger objectives than that. So they'd be able to look at these two stars and distinguish the two. So that's a basic example of introducing that idea. Um, Here's another one. A dark adapted eye has a pupil diameter of about 7 millimeters in a young person. This is something that changes with age. As you get older, your dark adapted pupil diameters get smaller. So it might drop to 6 or 5 in an older person. I don't know how you can actually test this. I'd be curious to see what mine happened to be. Um, when you go to an optometrist, they may dilate your eyes. They drop this crud into your eyes that make your pupils open up like crazy, but I don't think that counts because they open wider than they would in the dark. Anyway, suppose two radio towers with blinking red lights on top are separated by 20 meters. At what distance from the towers will an observer begin to have difficulty telling that there are two towers? And assume that the lights, blinking red lights on them have lambda equals 640 nanometers. So that's something that we know. Um, we're going to use a small angle approximation on this thing. I think we should, yeah, usually with these effects you can do that. But these are 20 meters apart. And we'd like to know at what distance would you still be able to see this? Oops, I think I'll use something else for distance. I'm going to use D, just lowercase d, to stand for the distance to this thing. Because we're going to have 20 meters over D. Now, usually you'll have that an arc length divided by the D is going to equal the angle between these things in radians. But if the angle is small enough, there isn't any difference between a straight line connecting things, or not much of a difference, and the arc length. So we'll just go with that. That's going to be equal to theta, and it'll be 1.22 lambda divided by the diameter of the, it's the diameter of the pupil of the eye, 7 millimeters. Well, this is a simple fraction equaling a simple fraction. I can flip both of them, and I can say that d over 20 meters is going to equal 1.22 times the, whoops, no, it's have to flip it. It's going to be 7 times 10 to the minus 3 meters divided by 1.22 times 640 times 10 to the minus ninth meters. So just applying that formula again, the 1.22 lambda over d is the best you can do angle-wise. So if I just take 20 meters and multiply by this, I'll know the distance. So 20 times. And we're not going to have a lot of significant figures on this thing. As in, we're going to have one significant figure. And I get about, wow, did it work out that well? It's 10 to the sixth. I think I may not have had a, whoops. Yeah, I forgot to put in a negative exponent for my, um, the diameter of my eye. Okay, that'll be better. Yeah, I was getting distance greater than the distance to the sun. So anyway, I get about 2 times 10 to the fifth meters, which is actually going to be about, what is that, 200 kilometers? So that's pretty good. That's quite a ways. But they are separated by a pretty good distance. Okay, I think I'll stop there, and we'll do some more with this tomorrow, but also a bunch of demonstrations before we start on the lab portion. There won't be a lab report for what we're doing tomorrow. It's just some problems to be solved. So we'll go with that. And I think I'll stop there, and I hope that today YouTube's going to process things faster than they have in the last week or so.